Welcome back, everybody, from lunch. I'm happy to see that you're not sick and tired of me yet. So yeah, understanding the Qt stack trace is something that I personally find quite useful, of course, when I'm working on Qt, but I think some of the details that you will run into when you are putting a breakpoint into your own application and looking at what's going on and what's all the stuff that happens before that breakpoint got hit, understanding that is usually also quite helpful for you when you are figuring out where things are coming from. So what we are going to focus on today is talking about a couple of principles of event-driven programming. Where do these events come from? We look a little bit at the multi-threading and QObjects thread affinity. And then when Fabian is going to take over, we are going to learn more about what happens when a signal gets emitted, and especially on the QML and Qt Quick side, then where is the boundary between C++ and the QML engine, and then also how do we get back from there. So first of all, let's start with event-driven programming. We're going to look at some typical startup code. This is hopefully something that you all have seen before, just understanding really what the process is here, what happens when we hand control over to the event loop, and what's waking up the event loop, and then looking a bit at event objects and where they come from. So I'll switch between Qt Creator and slide deck here. So don't be worried about this. This is going to be the size of the code and the size of the stuff that we are going to look at in the debugger. If you can't read this, there are a few spaces in the front, or pull out the binoculars. So this is the basic thing that you are going to look at when you are writing a Qt application. Let's start with the main function. This is nothing that you haven't seen before. I assume you instantiate your Q application object with the parameters that were passed into the process. You instantiate your application object structure, and then you show whatever you want to show, and then you hand control over to the event loop. Right? What does mean? You are letting the operating system decide what happens next. You are letting the user decide what happens next in your application. Qt is a framework. It's not just a library. It's the old adage of don't call us, we'll call you. So while nothing is happening, nothing is happening. Your application objects are then typically QObject subclasses. Perhaps in this case, it's a widget, it's a QMain window implementation. Yeah, you are constructing that as normal. There's nothing especially happening here. And then you might implement some event handlers. And this event handler in this case doesn't do anything particularly interesting. Let's put a breakpoint here and see what happens when we run this. Why is this event handler called? When I press the mouse into this window. That is the expectation here. All right, it's not a very interesting window. It's pretty empty. If I click in here, you can see that we are already a lot of stack frames, right? So that's exactly the point. A lot of stuff is going on under the hood before our code gets called. So before our code gets called, QWidget is responsible for actually taking the event and dispatching it to the correct event function. So let's make sure that we get that window a bit larger. QMain window here is handling a whole bunch of events in its event override. And that event override got called by the Q application implementation, which is responsible for dispatching the events to the correct object and to the correct function here, event, after sending it through some event filters. And if you go further down in the stack trace, we will at some point reach the territory of dark magic, which is where we are talking to the operating system's APIs. And in this case here, I'm running this on a Mac OS system. Let's make sure that we get as much screen space for that stuff as we can. So here in the event dispatching implementation of macOS, we are processing all these posted events, and further up in the stack trace, we are calling the macOS function that is basically waiting for the operating system to provide something. And that is, in this case, the NS app run. If you run the same function, the same code on Windows, you will find yourself somewhere here in the good old while get message dispatch message loop, or some variation of this. On Unix systems, you will be running here in a select call, waiting for something to happen, or some equivalent of this. And back here in stack frame number 31, that is where we are back in your actual, the code that you wrote. So 30 frames of stack between the one function that you're calling and the other function that you're implementing. So a lot of magic happening in between, or actually not really magic, it's really just talking to the operating system function that's responsible for selecting the next thing that happened in that process, the next thing that is relevant for this process, and then turning it into something useful. And there are a couple of things here on the way that I would like to spend some time on. So first of all, we have here a Windows system interface implementation where we are translating basically the event from a platform-specific event into a cross-platform event object. So that's one of the things that Qt is doing for you. Looking into the mouse event representation on macOS, turning it into a cross-platform Q event instance that is then dispatched through the Q event delivery machinery so that in the end of the day, Q widget and Q main window can translate it and call the correct virtual function implementation. So this is basically the general concept of why is code executed in your application, is because that's what Qt is doing. It looks at what's coming in on the operating system level, and then it calls the correct virtual function on your side, or in the objects that we provide in the Qt library. So many of our QWidget subclasses, of course, are then overriding those specialized event handlers or the more general event handlers and saying, okay, let's have a look, what does this event mean for me? I can update my state based on that. Okay, so that's the general idea of event handling, of waking up the event loop. While there is nothing happening, nothing is happening. Your process will use 0% of CPU. It will just sit there in an operating system kernel function saying, wake me up when something interesting is happening. Okay. So where do all these events come from? Yeah, I already mentioned, there are system-generated events. So for instance, when I just pressed the mouse in that window, macOS informed my process, there is a mouse event. The user clicked the mouse, do something about it. So that wakes up the event queue, it delivers the native event object, translates it into a queue event object, and then delivers that to us. That is all happening in what is called the QPA layer, the Qt Platform Abstraction layer, that is responsible for exactly that, translating user interface and some other events from native to platform, or to cross-platform, to Q event. It's also responsible for a couple of other things. Concepts like the whole windowing system integration. What is a top-level window in the first place? How do we position this? What is the understanding and the semantics of modality, for instance, on macOS compared to Windows? Trying to create a unified version of that so that you can write cross-platform code. That is all happening on the QPA layer. There is another source of events, and that's, of course, Qt events itself. If we are posting or sending events, that might wake up the event loop. Of course, in order to post or send events from Qt itself, we need to be already awake. We already need to be executing our own code. So I'm going to talk a bit about that later. And then there is the event delivery. We only briefly looked at that right now. Let's have a look at something a bit more interesting in that respect. All right, back to Qt Creator. Let's switch the active project here and look at that code quickly so that you know what's going on. All right, so this is basically the same startup routine, main function, creating a main window, showing it, passing event control to the event loop. The main window now is doing something a bit more interesting. It's actually creating a central widget for itself. It resizes itself, and then it gets shown later. We still implement mouse press event. Let's see what's happening there. And then the analog clock is, this is the grand premiere of our new analog clock implementation. That has been one of our widget examples that didn't look exactly like it has been 2020 plus for a while. So we put a bit of love and care into that one and made it pretty. So let's have a look at, first of all, stop the old process, of course. So here in this analog clock constructor, we are, for instance, starting a timer. Every second, we want something to happen. In this case here, I'm a bit lazy. I'm not remembering which ID this timer has, so this is a bit sloppy coding, but this is not an exercise in writing correct Qt programs. This is an exercise in understanding the stack trace. So I'm starting a timer here. Every second, I want something to happen. What will happen here is typically that my event function will get called. And I'm handling a couple of other events here. For instance, in this case, I'm calling the application palette change event. Let's see when that is happening. The mouse press event is also overridden in this analog clock here, just again to print something out. And then the timer event, that is the specialized event handler for timer events, is just updating the widget so that we get the new time actually rendered. Okay, so let's run this in the debugger. Grand premiere of the new shiny analog clock. Here we go. Okay, so obviously every second we are getting something to happen. It's painting the new time. That's exactly what we want. Let's put some breakpoints in here. So first of all, let's put one here, application palette change. Then we have the mouse press event. That's interesting, yeah? We had that already. If I put a breakpoint here in the timer event, it will fire immediately, so let's not do that quite yet. And then we have the paint event. The paint event just paints the clock. A lot of code, doing stuff. Putting breakpoints into paint event is something that can be a bit frustrating, because the paint event will be called whenever the active window switches between the application you want to debug and the debugger. That is not really a great way of debugging paint event code, so usually that's where good old qdebug and printfs and so forth are your tool of choice. So don't put breakpoints into the paint event, it's just not going to be a lot of fun. So we'll skip that here. The paint event gets called, like I mentioned, for many reasons. You don't always have to do that yourself. Like I just mentioned, when you change active window, QWidget will paint itself because it assumes that the palette will have changed. Active windows, disabled windows, inactive windows have slightly different colors, and Qt knows that, and it will say, okay, my state changed, I'll paint myself, your paint event will be called. So let's ignore the paint event for now, and let's have a look at the more interesting stuff. So first of all, let's put that breakpoint into the timer event, and like I promised, we immediately get it hit. And again, we are back in our stack trace. Again, bunch of stuff happening under the hood. We are again back in our event dispatcher. That is exactly the same call as we saw earlier. So yeah, we are passing control over to the operating system to say, wake me up when something is happening. And in this case, what's happening is that we are processing timers. We have an active timer source callback that we registered with macOS, and macOS said, here is a timer that's interesting for your application. We are translating that into something interesting. We are finding out what the object is that actually is asking for this timer event, and then we are sending this event to the respective object, which goes through the notification loop, through the notification process, and then we are back in the exact same code that we saw before. When the mouse press event was called, we're also in this function here, and then we are ending up in the main function. And this is interesting here. I overrode QObject event in my analog clock implementation, but I don't care on this level about the timer event. I'm caring about only the application palette change event, and then I'm calling the superclass. That is something that is important for you if you're overriding one of these general purpose event handling functions, QObject event filter. You are always well advised to call the parent class implementation, because the parent class might do something interesting with this type of event. It might, at the very least, like in this case, dispatch the events to the more specialized virtual handlers. So in this case, timer event. So in this case here, QWidget is implementing QObject event as well to call the various widget-specific event handlers. It doesn't care in itself about timer events, so it passes that one again to QObject, and then we are somewhere here in the weeds of QObject CPP, which is not interesting for us. So we are ending up in our specialized event handler, and now we are calling update, and that update will schedule a paint event for later. Okay, so that's one of these cases where your process is sleeping for a second, nothing is happening, no CPU is being used, we are waiting for the operating system to wake us up. And then, well, there is a timer, timed out, and we are therefore calling our virtual function. So let's disable this breakpoint, and let's look at some other ways to hit the breakpoint. When I click into the analog clock now, I will get my analog clock's mouse press event called, like I expect. I'm hitting the widget, I'm pressing into it, I'm getting the widget-specific, the class-specific mouse press event handler called. I'm not calling the parent class here, and there is a reason for this. Input events into Qt objects or events in general have two possible states, especially after they have been sent to the respective object. They can be accepted or they can be ignored. Especially for input events, that's important. Every event has that flag. It can be accepted or it can be ignored. What exactly that means and how exactly Qt treats the respective state is a bit depending on each event. For input events, the general rule is if the event comes back ignored from the object that it was delivered to, like in this case, the analog clock. If the event comes back ignored, it will propagate to the next level in the parent hierarchy. So if I'm ignoring this event here explicitly, the main window gets a chance. Okay? That is why I'm not calling the parent class mouse press event handler. These input events are delivered by Qt by default in the accepted state. And the default implementation of mouse press event, for instance here in this case, will ignore that event. That allows you to simply override the event handler, and by overriding the event handler and not calling the parent class, not calling the default implementation, you're implicitly accepting the event, which is exactly what you're doing. You're overriding mouse press event. You're surely doing that for a reason. You're surely doing that because you want to actually process that event. So we don't by default want to propagate it to the next level, because that might confuse your user if things happen on multiple levels of your user interface. So that's why we are not calling the mouse press event handler function here in our override, or the QWidget mouse press event handler function, I should say. If we would do that, we would get, let's do that quickly. And put a breakpoint into the parent object's mouse press event handler as well. So now, of course, we are getting the resize event, for instance. All right, mouse analog clock is here. I'm clicking into the analog clock. Now I'm getting hit on the implementation of the widget on the top of the stack, which is the analog clock. And now if I'm going into the mouse press event handler, the first thing it does is it ignores the event. It's that I'm the default implementation. I don't want this thing. Please propagate it if you need to, or if there is something to propagate it to. So now we can step over this. This is also where some of the pop-up handling is happening. In QWidget, you can make your widget a pop-up, which means it's a short-lived user interface component. If you're clicking outside of it, you want this pop-up to close. This logic is happening here. So let's step out of this. Okay, let's go a bit up in the stack trace now. So now we are back in our general event dispatcher override, and now we are in the notify helper that actually delivers the event. And here is exactly where this propagation stuff is happening in QApplication notify. QApplication notify is one of the virtual functions that you can override with care, because this is all events in a widget application are going through this function, and this is where this propagation is happening. This is where the semantic is implemented, that we say this event type gets propagated, this event type doesn't, under which conditions, and so forth. So if you want to have very fine granular control over what is happening with different events in terms of propagation, in terms of recording events, in terms of logging what is going on, what your user is doing, for instance, overriding QApplication notify is one of the options that you're having. Again, with care, because you might be breaking things very easily. And this is the while loop where we are basically saying for each widget in the hierarchy, let's translate the mouse event that we got to the mouse event that fits into that widget's coordinate system, deliver it to the widget, and then if it came back unaccepted, we continue to the parent widget and move on and try again. At some point, maybe it gets accepted, or at some point we hit the top level window and then we don't have anything to propagate anymore. Okay, so that's widget, that's event propagation. Very similar concept in Qt Quick, different implementation, because we don't have QApplication in widget in Qt Quick applications. And that's now we are getting the mouse press event in our main window. So that's the parent object of the analog clock. Analog click didn't want it. It ignored the event by calling the parent class implementation. Now the main window is getting it. All right. let's get back to the PowerPoint. So this is generally the idea of event handling and of event-driven programming in Qt. Most of the things, both in Qt widgets and in Qt Quick, happen basically along these line of thoughts. Now, threading, multi-threaded programming is of course then a way to make sure that while your application is busy with GUI work, something else should happen at the same time. If you have anything that is like costly, time-consuming, computationally expensive, if you're doing that kind of stuff in your GUI event, in your GUI thread, where your widgets live, where your event processing should basically as quickly as possible respond to the user clicking or to the user resizing or to the user interacting with your application, if you are not regularly and frequently return control back to the event loop, to that NSApp run call that is at the bottom basically of each stack trace, if you're not returning quickly from the processing of the last event to that level of the stack trace, well, then your user's input will not be processed until you are getting back there. And if your event handler runs a process, runs some computation, waits for some data for many seconds, that is not a great user experience. So the general rule is, if you do any of that kind of stuff, move it into a secondary, into a worker thread. Okay, so in Qt, any thread that you create can run its own event loop. It will be a slightly different event loop than the event loop that we just saw, because also on the operating system level, not every thread is allowed to process GUI events. We can't have every thread run an NSApp run loop, for instance. But yeah, there is an event loop that is taking care of stuff that's coming in from the perspective of Qt. So you have this idea of a thread and an event loop. For those of you who have been working with Microsoft Windows programming, that is what Microsoft is calling an apartment. It's a thread and an event loop, and in each of these threads that is running an event loop, you can have objects living there that are responding to stuff happening. And that stuff happening, just as with the GUI thread, needs to be something that's coming in from the outside. So Qt has at least one thread. That is the one that is running the main loop. That is the one that's calling your main function. That's where QGUI application lives, but that's where, yeah, most of your GUI objects will be living, or all of your GUI objects actually, and probably many of your other objects as well. If you are using Qt Quick, you have at least one more thread, unless you are running a single-threaded render thread, which is, yeah, an option, but by default you will have a separate render thread. And then there might be a couple of separate threads and a couple of dedicated threads in Qt, for instance, for populating a file system model or for doing some of the background work where we also don't want to block the user interface while we are doing that stuff in the framework. But by and large, unless you are creating lots of threads, there will only be the main thread to worry about, and perhaps if you're having your own implementation of quick items, for instance, a second thread where you need to make sure that you do only those things that are allowed in there. Okay, let's have a quick look at what that means in practice. And I'm first showing you a terrible way of doing things. But it's giving you an idea of what's happening under the hood. All right, we still have our analog clock. It's a slightly different version of the analog clock. I added a few more features there. And then, yeah, let's skip that stuff. We have a worker object here, and that worker object can do some work for us. It can find out when the next session starts so that we are not running over time. And instead of writing a lot of network code here and calling the REST APIs that our Qt World Summit app is using, I'm just saying, okay, let's wait for 5 seconds and then say, okay, the next session starts at 2:30. And then we are reporting that result back. But we also need to wake up this object somehow. We need to make sure that this work is actually happening. So in order to make that work happening, we can post an event to this object. Let's look at the code that's actually using this. So we have a worker thread, that's a Q thread down here. Okay, Q thread worker thread. And we have a worker object. And instead of just one clock, we can show multiple clocks now in a stack, which is nice because then we can overlay things with each other. And yeah, in the case of the user saying, find the next session, this is just a queue action living in the menu bar. In the case of that action being activated, we post the event to request the next session kind of information from that worker object. And that worker object then will do the work in that thread. And when it's done, it will inform us about it. Okay. Again, this is not how you should do. Don't do this at home. This is just a bad idea. But it shows you a bit of what's happening under the hood, right? It's happening that we post an event, we give that event some information so that the event handler can respond correctly to us. The correct way of doing this, I'll show that next, and then I will hand over to Fabian, who can tell us what's happening there. So let's put a breakpoint here, and let's put a breakpoint here, and let's also put a breakpoint into our response event handler down here. So again, what we are doing is when I activate that action from the menu bar, I post an event to my worker object requesting the next session. That is an event type that I implemented for that purpose. I'm telling it also who is asking for this information. In this case, that's this object. So that the event handler up here can unwrap that event object that it receives, can call the function that does the work. The function that does the work responds back and says, I got the answer now. And it knows who asked for the session because I told it. And it can send, or it posts that event back to the requesting object. I hope that's clear. It's, again, not how you should do things. All right, let's run this. All right, here's our clock. And we have now an action menu where we can ask for the next session. Okay, first of all, we get into our slot, into our signal, into our action handler. Again, Fabian will talk a bit more about what's going on here. And now we are posting this event to the worker object. Posting an event in Qt means we put it into the queue as one of perhaps many events that are living in that queue, and they will be processed one after the other. In this case, we put it into the queue of the thread that is running, or that the receiver object, in this case the worker object, lives in. The worker object lives in the thread here because we moved it into it. Okay, so in Qt you can create a queue object, you can move it into the thread where you want this object to do its work, and then it will receive event calls in the thread that it belongs to. You can also create objects in a thread, and then they will automatically be affine to that thread. But in this case, I make it explicit so that it's more visible. So by just posting this event, nothing is happening. We just put this event into the queue. If you look into the list of threads here on the right side, you can now see that we have a whole bunch of macOS internal threads that are not interesting for us. But there is also this one. Okay, that's what I mentioned. Worker threads on the operating system might have a slightly different event loop implementation than the GUI main thread. The GUI main thread has special responsibilities. This is a worker thread, so instead of hanging here in ns_app_run, we are hanging in a poll call. POSIX function to say basically sleep in the kernel until something is happening. All right. Now let's keep going. Somewhere. What happened? I'm in the wrong thread. And I hid my debugger view, and now I can't see anything anymore because it's very small. Excuse me? On the left. Yeah. No. Up. Click debug. Debug. Thank you.
Experience of debugging.
Absolutely. All right. So here we go. Unblock this one. So we are in our post event call. Let's keep going. We are expecting a call to hello. Sorry.
That's how our normal debugging looks like.
Yes, that is how debugging looks like usually. Okay, we are here, we keep going. All right, now we are in the worker event override. As you can see here, we were sitting in that poll call, something came in, and we woke it up because we posted an event to that thread. So when Qt posts an event to a thread, it also says, hey, there's actually some work for you, please wake up. So we are getting out of that poll call, and we are getting into the call to the worker receiver object event function. And what we are doing here now is, of course, we are calling this function that we want to call. We do the work, we sleep a little, and then once we are done, we report that result back to the event function of the object that requested this information. Okay? So now we are back in the main thread, we are back in the main window event function, and we are showing the result. And let's get back here. So now we see two analog clocks, one showing 2:30. So we have 14 minutes left. Very good. Just to make sure that you see that also without all the breakpoints, because the breakpoints are making this a little bit tricky to see that the user interface stays responsive while we are sitting in that 5-second sleep. So if I call here, show next session, the user interface stays responsive, the clock is ticking, the update calls are happening, bang. Now the network responded with the time of the next session. Again, this is not how you should do things. Qt gives you much better tools for this. So let's just quickly revert my code here by stashing all the things. Yes, I want to reload everything. So the correct way of doing this is, of course, to use signals and slots. We don't need to post events. We don't need to create our own event objects to encapsulate all this information that we want to ship to the other event. That is exactly what Qt is doing for us in the signal and slot mechanism that we have. If you emit a signal from one thread and the connected object lives in another thread, Qt is exactly doing behind the scenes what I just did manually. It encapsulates all the information that you want to emit into an event object. It posts that event, I think maybe we will see that soon, to the receiver's event loop, and then everything wakes up, the event information is getting demarshalled, and the function is getting called. So you don't have to do all this posting of events, creating of individual event objects, and so forth. So with that, I'll hand it over to Fabian to set up his machine, but we can use that time to see if there are any questions. Yes, please.
So when we use actual C++ to create different threads, then we cannot use connect signals. Or can
No,
we?
you can. Qt actually recognizes such foreign threads like native or standard library threads, JThreads, and so forth. It knows that this is another thread, and it will adopt that thread. It will create an internal data structure that basically allows us to do the exact same thing. If you are constructing an event loop, then in your native thread, it will be working like it should. Any other questions so far? Then I will step aside.
Right, and it's my time to take over. So clocks are pretty complicated if you work with computers. So the signals we look into are pretty simple for now. We have just 3 signals which are basically the same. And we have a small application. Don't run away, I'm the QML manager, but this part is still widgets. You can feel safe. And what do we have? We have an additional receiver object, which has exactly 1 slot to receive messages and does a bit of processing with them. Because Volker advertised that we have threading support, obviously we still create some object in a thread. But threading is also hard, even harder than timers. So for starters, we will begin with a sender object which lives in the same thread as our application to get a bit of an understanding what happens when we have signal slot connections. And obviously, one part that we need for the slot connection is a QObject connect call. We have basically 2 times the same setup where we connect our sender, like signal 1 and signal 2, to the receive message slot with the new style using function pointers. And then for sentimental reasons, we still have the old string-based connect here. Okay. The interesting part will be what happens when we reach receive message. So let's start our application. And this is using a debug build of Qt. So the traces you see here are more detailed than what you see when you use a Qt build from the installer. But hey, it's open source, you can build it yourself. So if you want to see all the details, you always can do it. And here we have basically 4 buttons, which trigger our various signals, and 1 button to which I will come a bit later. So let's click the one for direct connection. And we end up in our slot, kind of like we expected. And let's look a bit at the stack trace. So if you go down here, and I have to make that a bit larger for you, then at some point we see, okay, here's our signal. Sender signal 1. Oh, that was 1. So here is our signal emission code. Before I continue with anything else, I want to clarify one thing. There is an emit keyword here. It's marked yellow, so it's a keyword. And some people wonder, what does emit do in Qt? I hope I have your attention because I'm only telling it you once. Pay close attention. It does nothing at all. It's an empty macro. Why do we put emit there? Well, it's a hint to other readers of our code. If you step into this part, you end up in Qt. You might not want to go in here. However, you are in a session about Qt stack traces, so you're probably interested what's going on here. Let's dive a bit deeper. We are in a file which starts with mock underscore. So hey, I'm the maintainer of mock, so obviously I have to bring that up. This is the stuff mock generates for you. But to be honest, it's a very simple C++ function. You could write that yourself. You could use a macro, or you could use someone else's project with macros to get it. And what is going on here? Yeah, void pointers in C++. Scary. But to be honest, what we are doing here is basically some kind of type erasure. We get a QString, a conserv to it, in. And at some point, we want to call QMetaObject activate. And since I believe Qt4, we don't want to hardcode every Q type. Before, we could just like QMetaObject activate 1, 2, 3, whatever. But for generic code, well, we need to support all types. So what we do here is a very basic form of type erasure, where we create an array of void pointers, which are basically our data. And then we enter QMetaObject activate. QMetaObject activate is boring. It's just a forwarding function with scary atomics in it, but let's ignore them. Let's not focus on it. What it does is basically it checks internally or like there is at an earlier point there's a check whether we have signals by. That stuff that notifies you about signals. And yeah. So more interesting is we end up in do activate, which does the actual work. And in do activate, if we scroll a bit up, and maybe hide our debug view for now, what do? We try to retrieve a connection object inside a loop. So our objects store a list of connections. All connections we've registered. what we do next is we iterate over them and do some sanity checks, which I'm going to skip. We will do some thread checking, which is very interesting, but we will come later to it. And at some point we can wait. I have to scroll out a bit. Right, at some point we arrive at object.call. What is object? Object is basically our slot object. That happened when we created the connection with a function pointer. Basically, we created some object which stores various information, and notably it has a call method, and if we go a bit further down, we end up in call. Call goes further down by calling mimpl with the operation call. And then we basically just cast our function pointer to the correct type again. If you remember that array of that we have type erased, yeah, come on. The array we type erased, basically we convert it back to the actual type via some indirection. Here is the actual point where, here's the actual point where we reduce that conversion with template metaprogramming. That's why it looks a bit scary. But all it does is it converts our arguments that we type erased into the actual arguments, and we end up calling our actual function. Great. So that's basically all the magic that Qt does, and we can do the same with the string-based connection. If we do that, we end up in the same place. We mostly get back the same backtrace. The dispatching code will look slightly different. I might go into a bit more detail in it later, but for now we can skip it. And as you can see, we can go down, 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 and at some point we can see that we reach the point where we actually emit our, sorry, that's the wrong one, where we actually emit our signal here, emit. Great. So basically, if you want to debug your slots and want to know where you've been called from, just go down the stack trace. Great. Let's do that one more time with that button, which is Qt connection for some reason. And now we go down, 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 and there should be our signal. Wait, where's our signal? Q event loop? Is that Volker's part again? What happened here? Well, remember Volker talking about thread affinity? If you check our receiver object, which we connected to the second slot, then it has been called thread receiver, and it has been called thread receiver because it's been created in another thread. And as Volker mentioned, we do automatic scheduling of input events, and Connect does one more thing that we should mention here. If you have such a connection, it checks the thread affinity of your object, and if it's not living in the same thread, then we create an meta call event. And basically, that's how all of this works. Now we are running slightly out of time, I believe. 1 minute. And so I'm going to skip one, like the dangerous buttons that I had here. I want to show you one more thing because we've promised some QML. So here we have another project with a QML signal. And one thing we wanted to show you is, okay, sorry. I should set the breakpoint before I click on the button. How do you debug with QML? Well, what we do in our QML is we call a function defined in C++ called doSomething, where we can set breakpoint here. Let's debug that. I should select the correct project to run. And it's not showing. Great. A bit slow. If I click it, we end up here. And one important thing to note is if you end up in C++ from QML, use only C++. And the one thing I wanted to highlight is, in Qt Creator, you have the option to click on QML, load QML stack. QML stack line auf Deutsch. And if we wait a bit, oh, come on, why did it break? It should give you the QML stack, except I've broken it apparently again. Shouldn't have clicked on update. But basically, if you use it in a release version of Qt Creator, it should add the QML stack frames here, and you can click on them too. And then everything else is basically Signal Slots connection. And I'm already over time, so I need to stop here. If you have more questions about QML integration, come to me, talk to me later. If you want to know more about the integration of signals and events, come to me or to Volker. Thank you.